Hi everyone, this is Physics 2211, lab number 5, and this is kind of like a free-form capstone lab, so I decided to analyze the motion of a bouncy ball. So, the contents. First is the introduction, where we'll introduce the formulas being used, then the half-ball motion analysis using tracker, then a computational model using GlowScript, and lastly comparison and analysis. So to start off, the premise of this project is to model the motion of a falling object that's accelerating. I used a clip from another YouTube video that will be linked below, and it's basically a bouncy ball that bounces higher than it was originally dropped from the original drop height, which seems to violate the energy principle, so I wanted to see if I can make a computational analysis for that. The formulas being used are Newton's second law, F net equals ma, the force and gravity update formulas, the position and velocity update formulas, momentum principle, and energy principle. So this is the original clip.
It flying in the air way higher than where you dropped it from. In fact, the height that you drop it from almost doesn't matter in this case.
So this clip was inputted into Tracker, and it tracks the bouncy ball in the video and shows its relative position at different times. The data can then be used to calculate the initial velocity and energy changes to be used in the computational model. So this is the analysis of that. You can see that the calibration is set so that that's about 0.94 meters from this garage door, and you can see the point mass analysis tracking the ball in this scenario. You can also see the Y graph, the change right there, kind of models the bounce itself, and we're going to be using that and try to model that using computation. So in the model, the GlowScript Python code aims to predict the motion of the ball at the initial position and velocity of 0, and then the change of that over time. The corresponding code simulates what the path would have looked like realistically, or idealistically. The first model with just the basic ball and energy formula with no bounce, following energy conservation, and the second model includes the bouncing and tests with varying proportionality. So this is the first model that was created. It doesn't model the bounce, but it does include all of the energy formulas, as you can see here. The initial position is 1.1 meters taken from the tracker analysis, delta t is 0.034 seconds, and the acceleration due to gravity is 9.8 squared. These are all the energy formulas and the energy update. And that is the graph that is given, as well as the ball would have presumably hit the floor at this point. So while the first computational model does show when the ball hit the floor and kind of the first part of it, it doesn't include the bounce. So this computation also includes the bounce, but uses just the velocity and acceleration update with a more simplistic kinetic and potential energy formula. You can see down here so all of the constants are the same, and you can see down here there is a proportionality constant to model how much energy is lost during the bounce. Usually for a normal ball it would be under 1, and this model kind of shows that it's bouncing a bit less each time. But going back, our ball seems to exhibit a higher proportionality, so greater than 1, even though that's technically not possible using conservation of energy. I inputted a different number to see if that would model the ultimate bouncy ball a bit better. And that graph does seem to model it a bit more accurately, so that's the graph that we'll be using. So comparing the two graphs, you can see the potential energy curve on the simulated model seems to correspond with the Y value tracking from Tracker, so that seems to suggest that the computational model was effective. So analysis and errors. The initial model did not work because although the energy principles were applied correctly, I couldn't really work out how to incorporate the additional kinetic energy in the projected motion of the ball, and also unable to model the bounce correctly. If you watch the original video, the guy suggests that the extra energy is kind of generated from elastic energy from inside the ball, and that's really difficult to model. But in the second model, the bounce is modeled, but it appears that conservation of energy isn't followed due to how the values are shown in the graph. The total energy on the graph, green line, actually is showing the total energy from within the Bouncy system. But if you take into account the fact that some of the energy is lost to the surroundings or taken by the surroundings, it does make sense and the conservation is kept. Thank you and peace out.